Motors rely on magnets and coils pushing and pulling on each other to produce rotational movement. So surely it stands to reason that if we use bigger and bigger and bigger magnets and use thicker and thicker coils, we can make motors that are probably too powerful for Lego to handle? Well, let's find out. Now, previously I made some brushed motors like this baby motor and this bigger boy. And these motors use brushed contacts to control the timing and transmit power to the coils. But today, we're going to build brushless motors which transmit power wirelessly to the rotor, and the timing is controlled externally. And I want to see just how fast and how powerful they can be. To start with, let's build one of the simplest brushless motors that anyone can build at home, using only a couple of cheap components bought online. If we stick some of these powerful neodymium magnets onto a rotor, in this case alternating positive and negative facing outwards, now we have a magnetic rotor. If we then pop that onto a lift arm, and then add a couple of coils of wire on either side, now we have the makings of a single phase generator, or in this case, a motor. This reed switch then is the timer. The two magnetic pads in it make contact when exposed to a magnetic field, so when we bring some magnets near it, you can see it closing the circuit, creating a little desktop rave. If we then use this little 1.5 volt battery to power our motor. Okay, we've got to find just the right spot, and I think I've found it. There we go. So this is technically a brushless motor. Pretty impressive for only 1.5 volts. And I can speed it up and slow it down by changing the position of the reed switch slightly. To measure the speed of it, let's first see if this digital tachometer can actually be trusted. For each rotation of this little white Lego jobby, this should register 1 rotation on the tachometer. And indeed around 150 is what I'd expect for this little M motor. But my next motors are going to be spinning crazy fast, so I need to balance this spinning disc with another white blob. In this case, we'd expect the readout to double. And yes, this looks like about double the previous readout. So from now on, the numbers we see in the tachometer need to be divided by 2. So what speed are we getting with our reed switch motor? As it builds up to speed, it looks like we're getting around 900 on the tachometer, which is about 450 RPM on the rotor. Not bad for a 1.5 volt battery. Okay, well this is one way of making a brushless motor, but we're going to need to deliver much more power and in a more controlled manner. Now believe it or not, to make what I think is the world's smallest Lego brushless motor, all you need are these 20 pieces here. We'll start by making a teeny tiny coil by wrapping some thin wire around a pin. And from now, all of our motors will use 3-phase stators, so all of our coils will be in multiples of 3. For our stator, we'll pop these 3 coils into place here. So now we have our 3 coils. Okay, we'll pull the long ends out this way, and then the short ends we'll twist together and secure this little clip. Then we can bring the stator down here and pop it in place. Finally then we can take our rotor with these 4 magnets and stick it in here. Then to send the pulses from one coil to the next at the right frequency, we'll use this brushless motor controller. And yes, this thing is about twice the size of the actual motor. Okay, once we feed the 3 long ends from the coils into the controller here, to start us off, we'll use this not very fresh 9 volt battery. Okay, we'll control the speed with this dial here, and I may have to kickstart it, but let's give it a bit of juice and see what she does. Well, she wiggles. And there we have it, an absolutely minuscule Lego brushless motor. So we're about halfway. The controller is now sending alternating pulses to the 3 coils, and it uses back EMF as the magnets pass the coils to approximate the position of the magnets, so it kinda knows when to fire. Now this motor is very inefficient and very small, so even though it's spinning quite fast, the torque is terrible. But there is a way to improve its torque and efficiency. With this metal spoon, we can see the plastic pin with coil around it is completely unable to attract the spoon. But if we wrap the same coil around a metal core, the metal helps to concentrate and guide the magnetic field through the coil, massively increasing the flux, and allowing us to easily pick up the spoon. Neat! So let's make a minor revision to our baby motor and see if this will help us to improve its output. Our 3 metal core coils can fit in this cup, and we can pop this onto our new motor cage. Then let's do away with this crappy blue tack monstrosity and upgrade to a little 3D printed magnet mount. If we're gonna get some of these rotors up over 10,000 RPM, I'm not gonna risk these things flying off and destroying my apartment. Or me.
With our axle through the rotor, we can introduce it to the stator, and the magnets will grab onto the metal bolts holding it in place. This is really cool. I've wanted to experiment with brushless motors and improved generators for some time now. But as you've probably seen from my videos, it's really hard to mount magnets and coils onto Lego, often having to rely on blue tack or glue dots. And this becomes a major issue when magnets need to be spun up to tens of thousands of revolutions per minute. Which is why for this project I'm excited to get stuck into some 3D printing. Starting with this tiny guy, and going up to this monstrosity. Now, to be candid, I have absolutely zero experience with 3D printing, so building and setting up this beautiful little machine from bamboo was completely new territory for me. But I've got to say, the instructions and the little phone app that it comes with were super clear. We pop the base onto the gantry here, chuck in a few screws, slide on the purge wiper, flip out the touchscreen, and there it is, the Bamboo Lab A1 printer. Finally, we also have the optional AMS light system that hosts multiple filament spools at once. The AMS system can apparently accept any filament, but if you use Bamboo's filaments, it automatically understands what filament and what color it is, making the setup super quick. So for example, you can print 4 colors at once, or you can have the print continue if one of them runs out. Once the app is connected to the printer, you can either explore the marketplace and print some of the best designs out there, or you can do what I'm doing by making your own designs, like this multicolored propeller I designed in Tinkercad to test the blue, yellow and red on the AMS system. You simply drop the model into the Bamboo Studio app, select what filaments you want to use, hit the slice plate button, which then figures out how to print it, and then hit print. And we're off. We can check on the status of the print in the app. I've got to say, it's quite mesmerizing watching the nozzle dart back and forth. But this is a longer print, so I stepped out for a bit. So fortunately, I can use the Bamboo Handy app to check on the progress while I'm out. You can check out the video feed to make sure it's printing okay, and you can check on or even edit the temperatures of the printer, or even stop the print if you feel like there's been a misprint. Hey, voila! We have a beautiful multicolored propeller for our little motor. And for the motor itself, we'll need another little rotor. Now just before the print begins, it runs a quick series of tests and bed leveling so that there's no trial and error or human guidance needed. One thing I never fully appreciated about printing is just how fast the A1 printer head can move. This thing apparently darts around at up to 500mm a second. I can barely see it move. Now we're starting small with this little guy, but the A1 has this massive bed we can print on, allowing objects up to 256mm cube to be printed. And we'll certainly make use of this later with our bigger boys. And some of these toys for them. So check out the Bamboo Lab A1 at bamboolab.com, link below, and see how it can elevate your projects too. It's especially useful for LEGO projects like these. Now, the 1 to 3 gearing here should allow us to gain a little bit more torque out of it, which we'll need if we actually want to power anything. And there we go, it runs quite smoothly. The torque is definitely better than the first iteration, though it's still pretty weak.
Okay, let's see how fast it's actually spinning.
For now though, this is a pretty nice middle ground that still kinda works.
Half speed?
At half speed we're getting around 7,500, which is around 3 to 4,000 RPM.
Let's go full speed.
And at full speed this thing screams, wow, getting us to around 18,000 on the tachometer or around 9,000 RPM. I'll take it. Now torque straight out of the motor is still pretty weak.
Oh, that stalls so easy.
But at least with our gear down we can run this little propeller. Though I designed the motor poorly and it wobbles around a bit. Not great. Question is, can this tiny motor actually be used for anything practical? This weighted basket on a pulley can tell us if the motor can do any real work. If we use a serious gear reduction, we can hopefully turn those several thousand weak RPMs into a few powerful RPMs. Let's see if it can lift the empty basket.
Hey!
Oh, there we go, it can indeed do a little bit of work.
And what if I add one of these weighted bricks? 41 grams. Let's chuck you in here. Yup. Let's chuck in another. And another. And another. That's a total of 4. So the most this little motor can manage is just over 195 grams.
But if we're going to do some real work, we're going to need to upgrade to our next motor. This next rotor will host 8 much more powerful magnets. And this time we're going to double up on our wire coils, making the pulses sent to the motor more evenly distributed across the magnets. So now we have 6 coils which will be paired up to give us our 3 phases. If we nab a couple of these, and pop them onto a lift arm like this, we can take some of this 27 gauge wire and wrap it around each of the spindles. Moving on to the paired spindle on the other side. So this is our first pair of coils for one of the 3 phases. I quite like how compact this design is. Then for the motor itself, I'm going to make a little cage so that we can gear down the output for some increased torque if we need it. I expect this one to be able to spin very fast, but we can't pass huge amounts of current through it, so it probably won't have great torque. Once the coils are introduced to the magnet rotor, we can secure everything together, which is important when spinning these magnets up to thousands of RPM. Even the smallest speed wobbles can cause some pretty catastrophic explosions of Lego. To be consistent, we'll gear this one down by 3 as well. Now at this stage of filming, I found a new, much more compact 200 watt speed controller, meaning I can get rid of this ugly 500 watt monstrosity.
Okay, let's hook her up.
And the neat thing with this new one is that even with a 9 volt battery, this controller can bring us up into tens of thousands of RPM.
Alright, let's give her a quick try. And if I go up just a tiny bit more?
Whew, even the low setting is impressive.
Oh wow.
Even at 9 volts and a very low current supply, this thing is scary fast.
Let's see what the torque is like at low speed. Wow.
And even with it geared down, the speed is great.
Okay, let's see if I can actually stop it. Yep.
Now it does take a bit of effort, but it's definitely possible to stop it using just my fingers.
Wow.
Clearly the current supply from the 9 volt battery is severely limiting here.
I'm curious to know just what speed we're getting.
Let's test it without any gearing.
Okay, now I'm going to start this thing on the lowest speed it can possibly go by moving this literally just 1 millimeter, the tiniest amount I can. Okay, it's already moving. Let's see. About 5,000?
Well, about 2500 RPM is the slowest I can get it.
Okay, let's go up a tiny bit. Oh god.
To be honest, I was already nervous at how fast this was spinning.
8,400. Oh, I'm really nervous for this. 10,000. Maybe a little higher. Oh, I don't like this.
About 6,000 RPM.
I'm gonna stop there.
I don't think I've seen a Lego motor do these speeds. And to see if we can do anything useful with this ungeared speed straight out of the motor, let's yoink one of these printed saw blades with a Lego axle hole through it. And pop it into this little Lego circular saw table.
We'll start with some flimsy A4 paper. Just a little bit of speed.
And to be on the safe side, we'll bring this up to around 3,000 RPM. That should be enough. Well, as expected, regular writing paper is pretty easy for this to chew through. And the blade recovers speed pretty quickly. Not the neatest cuts, but it works.
Now what about some thicker cardboard?
Cardboard, however, poses more of a challenge. Again, the ability of the 9 volt battery to deliver enough current keeps this motor pretty weak on torque. But at least it's less dangerous. For now. Well, let's see if a different shaped printed saw can improve our cutting abilities.
Let's see if this does any better.
At these speeds, this one looks pretty vicious. By the way, if you like experiments like these with Lego and technology, feel free to subscribe or drop a like. And if you'd like to see more behind the scenes of how I make these things, my Patreon is linked below. Cheers!
Yeah, it seems to do about the same. I'm curious to see if the LiPo can produce more torque.
Now, in theory, the LiPo can deliver way more current. So when a load is added against the motor, it can handle more resistance before stalling. And hopefully this doesn't melt any of my thin coils.
The answer is yes. Made pretty short work of that.
So, can this help me make my sandwich? This meat will give me an idea of just how badly this might chew up my fingers if I accidentally touched it in motion.
Whoa!
Fortunately, it looks like even the thinnest portion of his ham isn't too badly cut by the sword.
Yeah, not amazing.
This means I need a bigger motor to make my sandwich.
I'm just gonna chuck all of these in here.
And out of interest, how does this motor fare with our weighted basket thingy? Now, looks like we'll need some more weight. This 1 kilo weight should pose more of a challenge. Even this looks like no issue. So, how about we try out its wind producing capabilities with this little printed 3-blade prop. It's pretty small, but because of this it can probably run very fast, even on a 9-volt battery with low current.
Wow. Okay, I'm hoping the propeller will provide some resistance. So let's see if I can max out the speed with this 9-volt battery. Okay, here it goes. Okay, that's maxed out. Very nice. Now, of course, this can go a lot higher with a higher voltage and higher current.
With our wind speed anemometer, we're clocking in at around 3 meters a second. Nothing crazy, but it does feel lovely. Okay, well, that was fun, but let's upgrade once again to our next size up.
Now we've got some of these nice beefy 15mm magnets.
I printed a couple of these on the A1 until I got some holes that fit these magnets very tightly, because the energy stored in this rotor wheel is going to be immense. Now this motor is our medium motor, and it's already at the limit of what I'm comfortable with due to this Lego construction. Similar to our previous motor, we'll build it around a simple 3-to-1 gear reduction. And of course, to drive it, we'll need some much thicker and sturdier coils. Now I suspect this design here is technically an illegal Lego building technique, but with all the ridiculous stuff I do with this Lego, it's hardly the worst offender.
Now I have a super strong 6-pole thingy I can wind our wire on.
For our coils themselves, we'll use some nice thick 24-gauge wire which can carry far more current. Which hopefully means we can get some real torque out of it.
Okay, let's hook her up. It's clear these wires are so much thicker. Okay, as usual, we'll start with a 9-volt battery. Let's see.
Oh, she spins up nice and easy.
Very good already.
Now this video unfortunately doesn't quite convey how intimidating this thing is in person.
Whoa. Okay, I'm actually curious if I'll be able to stop this with my hand. Okay, this is low speed.
Low speed with low current from the 9-volt battery.
Yeah, I can stop it with my hand. Let's get some speed.
Now this is expected. The battery probably can't supply more than just a few amps as the motor nears stalling.
Oh, wow. Gosh. That is quite a heavy flywheel.
But I bet with an even bigger propeller we can make use of this extra torque. So we can get rid of this gear reduction.
Let's see if it makes some wind.
This motor is definitely overkill for this prop, but it's quite a neat little desk fan.
Nice. Okay, I'm gonna see if I can max out this 9-volt battery. I don't like this. That's full speed.
Whoa, without a load, this keeps climbing to crazy speeds.
Now let's try a little speed test. Okay, this is a nice low speed. Okay, let's go up. Whoa. Oh, this is making me nervous.
And so with the rotor wheel weighing in at 63 grams, it's carrying a minimum of 26 joules of energy. And this looks like we easily hit over 10,000 RPM.
That is scary.
Whew. I did also want to try a motor with a metal core for the coils, and I started building it, but I'm already pretty certain the magnetic attraction will cause the axle to friction weld itself unless I can use a proper bearing. So I'm going to have to source that before trying it out. Now at this point I was really curious to print a new rotor that might increase torque.
Alright, we're going to use 16 of these 10mm magnets. Gosh! We'll get back to you.
In theory, double the magnets will half the speed, but even though these are smaller magnets, we may be able to increase the torque compared to the previous rotor with 8 magnets.
Okay, I'm going to use this same stator with all these coils on it.
I kinda prefer the idea of this rotor as it should be traveling slower with smaller magnets, so if one happens to escape, it'll be carrying much less energy. With our same 3-to-1 gear reduction, let's see if using a 9-volt battery outputs any more torque.
Okay, let's see. Wow, self-started immediately.
Of course, another benefit of more magnets is smoother coupling with the speed controller.
Honestly, the torque felt kinda similar. By the way, the scene looks slightly darker now because I've put up a cushion just in case a magnet flies off. It says low speed. Wow, even low speed has got us at about 7,000. Let's go up. Oh wow. And up some more.
And indeed, as scary as this is, we're getting around half the rotor speed, probably around 6,000 RPM.
Oh, I'm turning it off. I think we might have had a little bit of a speed wobble there. Not sure what happened. Yeesh.
Still not bad. So, let's see if we can use this extra torque to help me finish making my sandwich. I'm using the 3-to-1 gear reduction to allow the blade to really chew through whatever I feed it. The speed is already ridiculous. And this time with the LiPo battery, it barely even slows down during the flesh simulator. This is some lovely power.
Well, I can certainly cut my meat. What about some scallion for my sandwich?
Wow, that's pretty crazy. Once again, this cuts through it like butter. I don't think this motor is slowing down at all.
Well, it definitely has enough power, but these aren't very clean cuts.
And what about a heavy flywheel like this massive thing?
Fingers crossed.
Judging by the wiggles, this probably won't pose much of a challenge either.
Wow.
These speeds already make me nervous. It's so powerful I can rev the potentiometer and it responds almost immediately. I don't trust these blades holding on.
Nah, no way. Not taking that up higher.
But hey, why stop here? Let's go even bigger. This monstrous rotor wheel will host 8 of these ridiculously powerful 20mm N52 neodymium magnets.
Okay, this is the dangerous one. Well, that was way easier than I expected.
I expect this rotor to be total overkill for LEGO, but just for funsies, I'm going to build in a greater gear reduction to really make use of the power here. This has, I think, a total 15-to-1 reduction, which should yield some crazy torque. Though realistically, if you want a powerful motor for LEGO, it's probably better to take a smaller but faster moving rotor and just gear it down. What I'm doing here is silly. Once again, we'll use a weird and possibly illegal building technique to create the stator for the coils. We'll mount our 6 coils here, and this time we'll use even thicker wire at 17 gauge, which can carry huge currents without melting. I'm confident with this one we'll be able to handle massive current spikes during heavy resistance.
Okay, let's hook her up. God, these cables are thick.
We'll start at low current with our usual 9-volt battery. She jumps into action with only a fraction of the dial turned up.
Wow.
Even at these low speeds, the size and weight of this rotor is really quite something. And the gear reduction yields some crazy power output.
Yeah, there's no way I'm gonna stop that.
Remember, this is just the 9-volt battery. The LiPo should offer a ton more current and torque even without gearing. Now unfortunately, something I wanted to do in this video is test the current and overall wattage draw for each motor when they're near to stalling. But this video is already very long, so I'll leave that for a follow-up video.
So what about this guy?
So how about we upgrade to an even bigger propeller for this big guy? It should be able to push quite a volume of air. Though it still looks kinda small compared to this stupidly oversized rotor powering it. I just have to keep reminding myself that this is LEGO we're working with, so of course there are going to be inefficiencies. I've got to say though, this is impressive.
Very nice. That feels great. The wind speed isn't too high, but it is moving a large volume of air. This feels lovely and cool. Honestly, I'm way too scared to turn this up even higher. Those magnets are heavy and moving really fast. This makes for a lovely little desk fan though. Whew. And how are the coils feeling? Beautifully cool. Lovely. Well, there's a tremendous amount of power in this thing, but I'm honestly just too scared to push it higher. LEGO is not built for this. Well done.
There is one benefit to this sized motor though. I tried adding the biggest prop here to the small motor, And it certainly gets up to a good speed when powered by the LiPo. Blows a nice volume of air.
Good lord!
But after a couple of minutes, it died.
That is scary.
Turns out the thin wires were pushed a bit hard.
Great, that melted the contact a little. Damn it. Okay, we're gonna continue making our sandwich with our circular saw, using a 1 to 5 gear reduction, so it'll be moving slowly but very powerfully.
Now this should be able to slice through some serious stuff.
Okay, let's see.
But, by the way, this rotor weighs...
Yeesh, 213 grams.
Which means, if we were to rev up to 8,000 RPM for example, the rotor would carry 126 joules of energy, and an escaped magnet would carry 14 or more joules. Enough to seriously injure me. So I'm just gonna stick to around 2 to 3,000 RPM here.
Easy. What about this bone-dry bagel?
Now this bagel had been out for quite a while, and honestly, a real circular saw might have struggled.
Pretty good, but I think we need a different cutting tool.
Anyway, we power on. Now I figured this blade might exert more crushing power against the bagel. And it did take a few seconds, but at least the motor didn't feel even close to stalling.
Could probably do with a bigger blade actually, this did take a little while. But this thing is stiff as a board.
And speaking of bigger blades...
That is a chunky blade.
But to make sure this motor is truly able to drive it, let's upgrade to some metal parts. Now these guys should make sure that no matter what it tries to chew through, there will be no bending parts or broken gears. Even the rotor axle will swap out.
Ooh, they sound smooth.
We'll stick on our massive blade and secure everything to the table just in case. Now this thing is truly an overpowered monster.
Let's start with some thick cardboard.
Well, the moment of truth. The whir of the metal gears really is satisfying to listen to. Now this cardboard is quite thick, and even though the blades are slower, they're still comfortably chewing through it. What a beast.
Maybe a bean?
Yup, doesn't even register. Guess they makes for quite a good kitchen prepper.
Something a bit like a finger?
I guess my fingers aren't safe anymore.
Bit more bread?
Like butter?
What about a carrot?
And the carrot was the first thing that seemed to actually slow down the motor a bit. But with all that current, it still happily chomped through it.
Yup. That's a pretty clean cut. Nice. A little bit messy, but she cuts well.
If I'm honest, I really don't know what to do with all this power. But hey, at least I know it can help me make my lunch. So, burn up a tree. A big thanks to Bamboo for partnering with me on this video.